Okay, for today, we discuss on sorry, on sorry, start sorry. So for today class, okay, I will give some explanation on uh, the slope stability analysis. Okay. Then for the second lecture for today, okay, we will look on the stability analysis for the infinite slope. Okay. So then we will go for several example. Okay. Hopefully we can finish within 4 hours. Okay. So for tomorrow, we will discuss on the second type of slope uh, type, which is on the finite slope. Okay. So then we will go also for the several example to analyze the slope stability for the finite slope. Okay. So for this afternoon topic, okay, so I will give some explanation on the slope failure, okay, type of slope, process of failure, and type of failure. Okay. It's going to be a very general, but some technical explanation also will be included. Okay. So after complete this topic, okay, we will go for a very technical discussion. Okay, and also there will be some calculation involved. Okay. Okay. So a very brief uh, background of myself. Okay. So, okay, I graduated from the University of Sheffield in 2011. Okay. So this picture taken, okay, right after the Viva Bose sessions, okay, in 2000, at the end of 2011, if I'm not mistaken, on the October, okay. So this is my former uh, supervisor, Dr. Hurt, Dr. Crick as the external examiner from Manchester, Dr. Cripps, internal examiner, and Dr. Black, the my former second supervisor. Okay, so it took about 4 hours of discussions, okay, between Dr. Crick, Dr. Cripps, and myself. Okay. Alhamdulillah, I passed the Viva session. Okay, then after a month doing the correction, I back for good. Okay. Then I served to the UTM. Okay. So, and this picture is taken a month before I have submitted my thesis and waiting for the Viva sessions. Okay. So this is the landmark of the University of Sheffield. Okay. So Sheffield is located at the East Midland, about 2 hours from Manchester. Right. Okay, so this is the thesis title. Okay, I did my PhD on the behavior of weak soil reinforced with soil columns formed by the deep mixing methods. Okay, so this is the equipment used during my PhD program. Okay, it is a small scale physical modeling. So I construct for the soft soil ground inside this testing chamber. Okay, then tested it by applying uh, strain loads. Okay, on the soil sample. Okay, so at the same time, I treat the soft soil with what we call a soil semen column that I installed inside the soft soil. Okay? So by the use of these driving units, so I test the treated soil until it fail. Okay, the strength of the material has been collected or recorded using this load cell. The displacement during the testing has been collected by this LVDT. Okay, so during the testing, okay, I use this digital camera to capture the movements of the failure. Okay, so this is the image of the general shear failure mechanism, and it is similar with what has been proposed by Prandtl in 1921. Okay? So this what we call as this Prandtl failure mechanism. Okay? After 19 years, okay, we have the device or algorithm that can measure the Prandtl failure mechanism accurately. Okay, so after completed the test, I have carried out the dissections. Okay, to look on the column failure mechanism. I think due to the loading, vertical load. Okay. So then we found that there are a combination of shearing, bulging, okay, happen during the what we call as during the vertical loading test. Okay, that is little bit on my background. Okay, where during my PhD I did my PhD on ground improvement. Okay, so now after that, yeah, after serve for more than 14 years, after I've completed my PhD, so I also involved in several other research. Okay? So slope engineering is a part of my research work. Okay? So for today, we will discuss on the slope issue. Okay? So for the slope issue, specifically on the on the soil slope, okay? Not on the rock slope. All right. Okay. So slope failure, okay, is the movement of mass on slope. It can be falls, slides, or flow. Okay. So when we describe on falls, usually it is related to the rock type of structure. Okay. So slide, okay, it is most related to the soil, and flow. Okay, when the soil becomes like a liquid or mix a lot with water, so it will tend to flow, okay, like we call as a debris flow issue. Okay, so in slope failure, okay, basically the failure happened first. Okay, then we continue with a huge type of failure where we call as a landslide. Okay, so when we describe or differentiate between landslide and slope failure, usually for the landslides, it involve an extensive area. Okay? Okay? Since it's involve a very extensive area, it may cover with several mile slopes, which is less than 20 degree. Okay? And the movement is slow and gradual. Okay? So for the slope failure, okay, so it is very localized issue. Okay, so usually happen at a steep slope. Okay, so why it is happen at a steep slope? Okay, because when the slope angle is greater than the internal friction angle, okay, it tends to move, okay, or it tends to fail. Okay, that is why when we design for the slope gradient, okay, we need to make sure that the slope gradient is less than the internal friction angle. Okay. And for the slope failure, usually the movement is fast. Okay. Sometimes with no signs. Okay. Then this failure usually uh, contributed from uh, high rainfall intensity issue. Okay, so we can consider as a triggering factor caused by the rainfall. Okay, so the stability of a slope should be evaluated when slope movement due to additional loads or loss of strength is identified to cause problems. Okay, so we need to identify uh, what is the factor which contribute to the slope movements. Okay, can be external factor or it can be internal factor. Okay, so external factor can be caused by additional loads. Okay, can be caused by rainfall, looking high rainfall intensity. Okay, or internal. Okay, due to the movement or seepage issue that will create the strength of the material become weak. So it can contribute for the slope movement or slope failure. Okay. So this is the type of slope failure. Okay. As I mentioned, it can be a fall, okay, toppling, spreading. Okay. So usually this is more related to the rock type of slope. Okay. So we have sliding, okay, and also flowing. Okay. So for this is detachment of soil or rock fragments that fall down a slope. Upper, this is a forward rotation of soil or rock mass about and exists below the center of gravity of being displaced. Okay. So we have slide. This is downward movement of a soil mass occurring on the surface of rupture. Spread. This is form of slide by translations. It occurs by sudden movement or water bearing seams or sand or silt or blown by clay or loaded by fill. It usually happen at an infinite type of slope. Okay. Flow, this is downward movement of soil mass similar to a viscous fluid. Okay. So this is usually happens when the area is near to the river stream. Okay. So it uh, potential to uh, become like a fluid, okay, when it mixes with the water. Okay, so then there are a lot of cases where the incident of the breeze flow happened at the hilly area. Okay, uh, slope types. Okay, we have here natural slopes and man-made slopes. Okay, so for the natural slopes, usually related to the long-term process and short process. Okay, and it can be described as a formation of hill and valley. Okay, or simple terms, it is a natural existed. Okay, which is not from the man-made activities. Okay, so meanwhile for the man-made slope, okay, so yeah, we do some development and the need for excavations or cutting. Okay, so in that case, okay, we have disturbed the natural slope, so then we can call as a man-made slope. Okay, or we do a filling and then, for example, to construct for the embankment or earth dam, so then that is also considered as a main slope. Okay, so this is example of excavated slope. Okay, so the actual slope is represented by this dashed line. Okay, so then for the development purpose, so they do the cutting. Okay, and then uh, they have actually have disturbed, okay, the stability of the natural slope. Okay, so then for the man-made slope, uh, we need to analyze it and make sure that the factor safety is greater than 1.5. Okay, okay, that is based on the conventional approach. But now, uh, some of the analysis, okay, we use the Eurocode 7. Okay, so for the Eurocode 7, we need to make sure that the over design factor should be greater than 1. Okay, so we discuss on the approach of the EC7. Okay, and also show the calculation based on the conventional uh, methods. Okay, so for the conventional methods, we need to make sure that for the man-made slope should be greater than 1.5. Okay. Okay, so this is the embankment slope. Okay, well, this is for the earth dam structure. So this is the slope that construct for this earth dam structure. Okay, so for the embankment slope, okay, uh, the most critical issue is on the foundations itself. Okay, first we need to make sure that the the bearing capacity of the proposed uh, area for this embankment slope is capable to cater for the embankment structure. Okay, so once we found that it is suitable, okay, so then we need to construct it um, based on the JKR specification. Okay, so we need to compile it well and then make sure that the degree of the slope or the angle of the slope, either we use uh, 1 to 2 or 1 to 1.5. Okay? So it is not advisable to use 1 to 1 because what I've mentioned before, if 1 to 1, so the degree of the slope, it will be 45 degree, okay? And usually it is more than what we call as the internal friction angle of the slope of the soil material. Okay. So usually there will be no issue for the slope, okay, stability of the slope. The more issue is related to the foundation stability, okay. So there will be one topic discussed on the uh, construction of the embankment slope. Okay. So the issue for the earth dam is more related to the seepage issue. Okay. So because at the back of the earth dam, okay, used as a water reservoir. Okay. So then we need to look on the effect of the seepage, okay, to the stability of the earth dam structure. Okay. Okay. So now we look on the slope terminology, okay, to describe the meaning of each the meaning of each geometry or each layout for this slope. Okay, so yeah, this we call as a slope height. Okay, so then slope toe. Okay, slope ratio. Okay, horizontal to vertical. Okay, so means that horizontal is, let's say if this is 2, so 1. So we describe as a 2 to 1, okay, or 1 to 1, or 1.5 to 1, okay. So then we have a terrace or berm, okay. So terrace in UK, berm, terrace in US, berm in UK, and from UK, okay. So for every 6 meter heights, usually we need to construct for one berm. Let's say if we have 10 meter height, so then for every 5 meter height, we should construct for the berm. So means that if it is more than 3 meter height, so it is suggested, is it more than 6 meter height, it is suggested to have one berm. Okay. And if I'm not mistaken, the length or the width of the berm should be 2 meter. Okay. Then what we call this is this slope face. Okay. So top of scarp and surcharge. Okay, on the top of the slope. Okay. So this is the slope terminology. Okay. So we have toe, top, uh, berm, terrace, slope ratio, face, and surcharge. Okay, principle of slope stability analysis. Okay, this is a simple analogy. Okay, sliding will occur if the shear stress develops exceeds the corresponding shear resistance or shear strength of the soil. So in this case, failure is assumed at a certain plane. Okay, so just imagine this is a block of soil. Okay, with the weight from the block and angle of the alpha, for example, this is alpha, okay? So it tends to push down the block downward, and at the same time, there is a shear strength, okay, that uh, resists, can provide the resistance uh, to hold the block from moving downwards. Okay. So usually for the slope stability analysis, okay, we may use equilibrium methods, LEM. Okay, so linear method, we derive based on the resistance over driving. Okay, so if the resistance is greater than the driving, okay, so means that the factor safety is greater than 1. Okay, however, 1 is not enough. Okay, so we need to make sure that the factor safety should more than 1.25, okay, or more than 1.54 man-made slope. Okay, based on the conventional approach, we doesn't apply for any factor safety as place. So after we complete calculated for the shear strength and also the shear stress, so then the ratio between the shear strength over shear stress is the factor safety. Okay, so that we need to make sure that the factor safety is greater than 1.5. Okay. However, for the EC7, okay, so we implement several partial factor safety. Okay, so toward the end, the ratio between the shear strength and the shear stress is considered as over design factor. Okay, so if the over design factor is greater than 1, so is comply with the EC7 approach. Okay. Okay, I just want to some different type of material. Okay, but basically, it try to describe what happened when we have a sloping different sloping level. Okay, for example, for this case, the top of the first layer is unconsolidated sediment. Okay, and the second layer is as a sandstone. Okay, so then it has a sloping. Okay, then we try to look the how the derivations of the material between the sediment and sandstone, okay, that can be used to determine the stability of these two material. Okay, so what hold the sediment in place and what pulls down? Okay. So then we put a schematic diagram in where we assume the sediment is in block, where the sandstone is the plane of the slope. Okay, so then this block represent with the width, and it has an angle to represent the slope. Okay, so the width is concentrated at the center of the block due to the gravity force. Okay, then theta is the slope angle. Okay, so that is the W, the width of the block. Okay, the width always points straight down. So we consider the width is force as well. Okay, so then we resolve the force into two components. Okay, the first one is parallel to the slope. Okay, so we use a notation of FP. So with the use of trigonometry, okay, so then the theta from the slope angle is equal to the theta as shown here. Okay, so based on simple trigonometry, okay, the FP is equal to W sine theta. Okay, hope you still remember how to use the trigonometry. So yeah. So if this is theta, okay, so then yes, we have sine, cos, tangent. Okay, so then this is hypotenuse. This is adjacent, this is opposite. Okay. So for sine, O over H. Cos, adjacent over H. Tangent, opposite over adjacent. Okay. So for this case, to get the FP with the W, Okay, so sine theta, this will be your FP, sine opposite FP. So then this will be W. Okay, so then we get W sine theta. Okay, opposite over hypotenuse. Okay, the force parallel to the incline FP is what pull it down the slope. Okay, so we call it as a driving force. Okay, then a simple explanation to describe what will happen if we have small angle and large angle. Small pulling force, okay, definitely if the angle is steep, so it contribute to large pulling force. Okay. So slope mechanics and material strength. Okay, then later on we look on the normal force acting on the what we call on the slope plane. Okay, so for the normal force, it represent by Fn, which is W cos theta. Okay, component of which normal or perpendicular to the slope. Okay, so the normal force Fn is what contribute to the force, to a force that resist movements down the slope in part control the material strength. Okay. So, for example, when the block is horizontal, where there is no angle, which is angle is equal to 0, so then the Fn is equal to W. Okay. So then we try to pull. Okay. When we try to pull it, okay, so there will be a reaction that called as a friction force. Okay. So the coefficient of friction quantify the degree of roughness between two surfaces, bottom of the block and the horizontal surface. Okay. So if we have two different type of material, so it means that the bottom of this block and also the friction that occur from the horizontal surface. Okay. So then if we try to pull, so it have the friction force for the block, okay, from move. Okay, let's say if the block and the surface consists of smooth type of made from smooth type of material, okay, so we can assume it is a low coefficient of frictions, okay, as compared to a material that is rough, okay, so definitely it show a high coefficient of frictions. Okay, so this is based on the coefficient of friction change with based on the geological material. Okay, let's say for clean, okay, the friction new, okay, we got as a new is 0.1 to 0.3. It's sand 0.4 to 0.8. Okay, if rock, the friction mean is a little bit high. Okay. So in soil, okay, if it's a material is both of the material is soil, so we can call it as a internal friction angle. Okay. But this is to show the different, if there is a two different type of material, okay, so it's represented by the name of coefficient of frictions. Okay, the coefficient of friction is also controlled by mineralogy. Okay, so basically, quartz is strong, olivine is not. Okay, and grain shape. Okay, angular has a high coefficient of friction compared to rounded. Okay, so packing arrangement. Okay, tight or dense is a high coefficient of friction compared to loose materials. Okay. So the magnitude of Fn increase the interlocking of the two surfaces because the force push the imperfection together, make it harder for the block to slide. Okay, this increase the friction force. Okay, so the normal force from the block, okay, uh, will contribute as well to the friction force. Okay, that hold the block, okay, from moving down. Okay. So just to show what will happen if we increase the Fn, so it will increase the friction force. Okay, the magnitude of the Fn increase the interlocking of two surfaces because the force push the imperfection together, making it harder for the block to slide. Okay. So basically, to increase the friction force, okay, so then uh, we need to increase, okay, the normal force and also the coefficient of frictions. Okay, mechanical friction keep the block from sliding. Okay, so then for the internal material properties also contribute to the stability of the slopes from this block to moving down. Okay, so usually in soil or in any type of material, okay, they have what we call as a cohesion. Okay, so molecular cohesion between the grain also contribute to the material strength and keep the block from sliding. Okay, usually for the soil, okay, they have combination between cohesions and internal friction angle. So we call it as a C and P. Okay, usually cohesions obviously uh, exist in fine type of material like clay and silt. Okay, while uh, internal friction angle, okay, usually have a high value, okay, when the material is uh, formed like a sand or granular type of material. So this is example to show how does the cohesion work, okay? And it also contributed by the moist, okay, inside the material. Okay? So moist sand has a strength. Okay? So the strength is created by molecular force of attraction between sand, water, and air. Okay? So calcite and silica and cement that bind mineral together is another form of molecular cohesions. Okay, so means that inside any type of properties of material, okay, it has cohesions, okay, and also have frictions. Okay, so the stability of the slope is analyzed by comparing the magnitude of the driving force to the resisting force. Okay, so from there, we derive the factor safety, okay, based on the resisting force over driving force. Okay, so this is what we call as a limit equilibrium methods. Okay, so based on the resisting force and driving force, okay, uh, the equations, okay, that um, that develops, okay, from this driving and resisting force, okay, is W cos theta times mu plus C. Okay, but this is not for the soil. Okay, for the soil we may use what we call as the Moore column model. Okay, where we have Cn, sigma, and also phi. Okay. While for the resisting, while for the driving, okay, so we, that is the equation where W sines theta, okay, it rely on the width of the block, okay, and also the angle of the slope. Okay, so at a low slope angle, FP, which is the driving force, is small, and Fn and hence F are larger. Okay, so basically the Fn is higher. Okay, when the low slope at the low slope angle. Okay, so in that sense, the factor safety is give a higher value, which is more than 1. Okay, what will happen if we have a steep slope? Okay, so for the steep slope, definitely the force from the driving will become greater. Okay, and then if the force from the driving is greater, so it may reduce the factor safety, and the factor safety will be less than 1. So that is the simple explanation on the slope by using a block uh, model on the slope plane. Okay, so resisting force over driving force, okay, is less than 1. So the slope fail if the factor safety is less than 1. Okay. Okay. So from there, okay, we go for the limit equilibrium methods. Okay, so method of analysis is limit equilibrium method. Okay, so um, yeah, if you're familiar with software, okay, so at the market we have GeoStudio. Okay, so the GeoStudio for the slope W usually they use the limit equilibrium methods. Okay, so at the same time they also have finite element methods. Okay, from the sigma W. Okay, so for the limit equilibrium method, we can identify what we call as the factor safety. Okay, while for the finite element method, okay, we can identify the deformations. Okay, so we need to know what is the allowable deformations, okay, um, to identify the stability of the slope. Okay, so it doesn't mean examine the slope stability only by using the limit equilibrium method. We also can use what we call as the finite element method, okay, to examine the stability of the slope. Okay. Okay, for under the limit equilibrium method, okay, the factor safety is considered as the shear strength. Okay. Or in the previous discussion, okay, we consider as a resistance force. Okay? Is the shear strength at the time of failure, tau F, compared to the stress? Yes. Derek? Okay, factor safety is the strength at the time of failure, tau F, compared to the, oh, I thought you want to ask question. Compared to the stress acting at the plane, tau M. Okay, so if Fs is equal to 1, then the slope is in a critical conditions. Okay, so means that critical conditions where the slope is equal to, and where the factor safety is equal to 1. That is why it's not suggested to say that the slope is stable, okay, when the factor safety is equal to 1. Okay, okay. Okay, so then, okay. Yeah, you just imagine if you design your slope, okay, at the factor safety of 1, okay, suddenly if there are additional loads, okay, uh, rest on your slope top, okay, on the slope surface, okay, so it can increase the shear stress, okay, the acting on the plane. Okay, so then it can contribute to the instability of your slope structure. Okay. At the time of failure, the stress strength of the soil is fully mobilized along the failure plane. The stress strength is represented by the Mohr column criteria. Okay. So for the shear strength, okay, which is the tau F, okay, uh, we can analyze our slope either by using a total stress analysis or by using an effective stress analysis. Okay. Okay. Usually, when we design for the slope, okay, we go for the effective stress analysis because we want to design this for the long-term analysis. Okay. Uh, Definitely, when we design based on the long-term analysis, the factor safety is less, okay, as compared to the total stress analysis. Okay. So means that when we want to when we want to design for the slope, okay, so the soil parameter or soil properties result from the laboratory, okay, we should request for the result based on the effective stress uh, value. Okay. So for example, we need to ask for the SI contractor, okay, to carry out for the what we got for the consolidate undrained test. Okay, for the triaxial, for example. Okay. So at least we can use the C and P value, which is under effective stress. Okay. So in relation to the shear strength parameter to be used in the slope analysis, it's important to know the time when the most critical state occurs. Okay. So if the most critical condition is predicted at the end of its construction periods, so then short term, which is the short term, then the total stress concept is more appropriate. Okay? So on the other hand, if a critical condition is predicted in a long-term situation, then the effective stress concept is to be applied. Okay? This depends on the type of slope in question and on the type of soil. For example, the most critical condition of excavated slope is long term, while the most critical condition for embankment is short term. Okay, but for my suggestions, it's better to uh, carry out the testing based on the long term analysis or the effective stress analysis. Okay? Because in the effective stress analysis, we consider the pore water pressure. Okay? But in total stress, uh, the value for the effective stress plus the pore water pressure included during the analysis. Okay, for slope made of low probability such as clay, the undrained assumption may be more appropriate since the distribution of pore water pressure will take a long time. Okay? For highly permeable soil such as sand, where drainage takes place almost immediately, we use effective stress parameter, which is C and P. Okay. In relation to the type of the failure surface, the subsequent parts we deal with stability analysis for infinite slope, which is related to the transitional type of failure, the analysis of finite slope with planar surface of failure and circular failure for the undrained conditions. Evaluation of slope stability for a more complex situation should be analyzed using method of slices. Okay. Okay. So yeah, it depends on the type of material. Okay. For example, as suggested here, if we deal with clay material, okay, low permeability, so the undrained assumption may be more appropriate. Okay? Since the distribution of water pressure will take a long time. So in our analysis, especially when we use a numerical modeling, okay, so then we need to assume for the clay, we use the undrained, okay, while for the sand, okay, we use a drainage type of material. Okay. So the type of failure surface, for example, when we deal with infinite slope, okay, so then we need to use what we call as a linear failure plane methods. Okay? Later on, we discuss on the infinite slopes uh, on how to analyze the or to determine the stability for the factor safety. So the analysis of finite slope with planar surface of failure, circular failure for undrained conditions. Okay. So for the finite slope, okay, later on I will explain what is finite and infinite slope. Okay. So if we deal with a finite slope, okay, so we can use either linear failure plane methods or we can use a circular failure plane approach. Okay. So for the parameter used in analyzing the slope stability, okay, so we may use the CMP, okay, uh, to determine the stability of the slope. Okay. Uh, okay, and this is limited to saturated soil mechanics only. Okay. So if we deal with unsaturated soil mechanics, okay, so then there will be a lot of parameter that we need to consider in our analysis. Okay. So this is limited to saturated soil mechanics only. Okay. Process of slope failure. So we have several causes contribute to the slope failure. Okay, the first one is slope inclinations, the type of earth material, vegetations, okay, loss of shear strength okay, due to weathering, liquefactions, water. It can be from infiltration of rainfall and the movement of the groundwater level. We call as a seepage, climates, and additional load of field heights. Okay. So then we go one by one. Okay. Then the another one is excessive for water pressure. Okay. Role of slope inclination. In slope angle is a measure of the steepness of a slope. Slope gradient. So for a steeper slope, it may increase the driving force. Okay, steep slope, as you said, with rockfall. Okay, sub-arid to arid environment. Okay, also may contribute uh, to the to this slope inclinations issue. Okay, arid environment is more related to a dry conditions, while sub-arid is a little bit moist compared to the sub-arid. Okay. So, rule of earth material, okay, slope formed by weak rock such as shale or have thick soil deposits, typically filled by rotational slides. Okay. Slope formed by hard rock, typically filled by transitional slide. Soil slip occur above bedrock and filled by transitional slide. Okay. So for our discussion, okay, we will go for the soil slope, okay, which is slope that consists of soil material. Okay, so there will be only the difference between the 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 stiffness and the strength of the material. Okay, so there will be no combination between soil and rock material. Okay, role of vegetation in subhumid to humid environment. Vegetation is thick and abundant. Okay, landslide activity include deep complex landslide, earth flow, and soil trips. Okay. Vegetation influence slope stability by providing a cover that cushion the impact of rain falling on slope and retards erosion on surface. Okay, so that is the benefit of having vegetations. Okay. Vegetation has root system that tend to provide an apparent cohesion, which increase resistance to landsliding. Okay. So usually to prevent from the erosions happen at the slope surface, so they plant a special grass, okay, on the slope surface, and the grass also have a very thick root system that also can increase the stability by providing a tensile strength on the slope surface. So, however, vegetation adds weight to the slope, increasing the driving force. Okay, so make sure that we need to trim or do a maintenance. Okay, to ensure that the weight of the slope, weight of the plant or tree doesn't add additional loads to the slope structure. Physical and chemical weathering. Um, it also may contribute to the weakened slope material, okay, and it can decreasing the resisting force, okay. So, for example, you have 6 grade of weathering material from the fresh rock, okay, to the residual soil, okay. So, due to the physical and chemical weathering, okay, uh, the grade of weathering can be increased, okay, and it can contribute to the weakened slope material. Okay, so if we are dealing with grade 6, okay, so this consists of residual soil, okay, so then uh, that is that represent the start of the soil slope. Okay, so when we want to analyze, okay, uh, based on the soil slope, okay, so then we use uh, a different type of and different type of what we call different type of software compared to the raw type of slope. Okay, water can affect slope stability by shallow soil slip can develop during rainstorm when slope becomes saturated. Okay. So that is related to also related to the erosions. Okay. Slump or transitional slide can develop month or year after slope is saturated. Okay. Water can erode the base of the toe of the slope, decreasing slope stability. Okay, so that is the role of water, which is can affect the slope stability. So timing influence the amount of and timing of water in form of water or snow, influence type and amount of vegetation. Okay, and the triggering mechanism, okay, that also can contribute to the stability of the slope. The first one is rainfall. Okay, the intensity of the rainfall, you can increase the pore water pressure. Okay, erosion removal of toe supports increase load angle. Earthquake loading, okay, may contribute to the dynamic force and make the slope, make the material, especially for the granular material, become like a liquid due to the liquefaction effect. Construction activity, okay, at the toe, surcharge loading at the top, and rapid drawdown, okay, for example, due to the dry season, okay, it can make the water in the reservoir to decrease, the level water and the reservoir to decrease. So it can contribute to the stability of the reservoir slope structure, okay, and can make the reservoir slope structure to collapse. Okay. Okay, there is a factor that contribute to the slope failure. Okay, now we move to the type of failure. Okay, we have ridge failure. Is the soil mass movement due to external force? Okay, this type of failure usually occur on the weak plane or weak joint. Okay, so usually when we heard about joints or plane, okay, it is more related to the rock structure. Okay, so then we have secular failure or non-secular failure, where secular failure are associated with homogeneous soil conditions, and non-secular failure are associated with the non-homogeneous condition of heterogeneous type of material. Okay. So for circular failure, okay, and non-circular failure, okay, usually related to finite slope. Okay. And transitional failure occur when the form of failure is influenced by the presence of weak layer. The failure surface tend to be plane and roughly parallel to the slope surface. Okay. So for this transitional failure, it is related to what we call as an infinite slope. Okay. Okay, this is the type of wedge failure. So for this wedge failure, okay, we can see that it fail in a block due to the weak joint occur at the rock slope structure. Okay. So this is a circular failure or non-circular failure. Usually happen or occur at finite slope. Okay. So this is we can call as a finite slope where it has uh toe at the bottom, surface and top. Okay. So to analyze the stability of this finite slope, okay, usually we need to use a non-circular or non-linear method, okay, by construct the arch on semicircular shape, and either we can use what we call as a Porter stress approach or method of slices. Okay. Hopefully tomorrow we discuss on this issue. Okay. So this is for the circular failure. Okay. So if it is a perfect circular failure, okay, means that it consists of homogeneous soil condition. So if it's not a perfect uh, circular failure, so it has a combination of multi-layer of soil. For example, okay, this is soil number one. This is soil number two. Okay. Okay, so this is an example of a failure happen. Okay, a little bit we can find that there is a type of circular. Okay, uh, show okay on the failure slope. So okay, in order to treat this type of circular failure, okay, so usually we need to what we call as we need to construct like this, like a stair. Okay, then then we do a compaction again. Okay, okay, this idea to make sure that uh, the what we call the new material stick uh, with the existing material. Okay, all right. Then another type of failure is transnational failure. Occur when the form of failure is influenced by the presence of weak layer. The failure surface tend to be plain and roughly parallel to the slope surface. Okay. So in this case, we call this as a infinite slope. So we assume there is a weak plane, okay, occur, okay, inside the this infinite slope, okay. Then we also assume that the thickness is similar, okay, throughout the slope, throughout the slope length, okay. So with that assumption, okay, then we can we can uh, analyze the stability of the infinite slope, okay, uh, by using the limit equilibrium methods. Okay. Okay. Due to the length of the slope surface uh, relatively greater than the height of the slope, okay, so it's very difficult to examine the transitional failure. Okay, so is that for the infinite slope? Okay, we can see that the length of the slope surface relatively greater than the heights. Okay, so that is why it doesn't have that we will not consider this toe and this toe and top of the slope. Right. Okay. Uh, then another additional type of failure. Okay. So the A called as a transitional slide, similar to what we discussed before on this example. Okay. So rotational slide, okay, happen at the base. Okay. So then we have toe slide C, okay, where the slope failure, okay, is located from the toe, okay, to the top, okay. So then we have slope slide, okay, also from the rotational slide, okay. Then we have a flow slide, okay, and the last one is block slide, okay. So for the finite slope, okay, okay, based on the literature review, based on the reference book, okay, um, we also can consider the what we call the translational slide, okay, if we are focusing on the slope surface, okay. For example, okay, or like for example for this one, okay, uh, due to it has a two layer of weak soil, okay, so it tends to have a transitional slide. Okay, okay, failure modes. Uh, the from a very slow lateral speed to a very fast. Okay, uh, and also the velocity of the mass movement also increase. Okay, from the lateral speed to the rockfall failure. Okay, this is an example of toppling instability. Okay, this is example for a debris flow. Okay, this is example of a rotational slide, okay, where it has a zone of depletion and zone of accumulations. Okay, so usually it's happened from the top or scalp. Okay, so we can see this is the surface of failure. Okay, and then there are no failure happen at the zone accumulation, but the soil has been displaced, okay, up to this area. Okay, so this is the tip or toe. Okay, this is example of the block slide. Okay, where the movement of the block of the soil, okay, move in lateral or in horizontal direction. Okay, slide, okay, down the downslope movement of coherent block or earth material. Okay, slump is starting from the top, sliding along curved slip plane, producing slump block. Fall is from the rock fall, from vertical. Flow, it is more related when the soil mixed with like a water. Okay. So subsidence, where a sinking of a mass of earth material below the level of surrounding material. Okay. So this is more related to the settlement. Okay. So this is example of slump failure. Okay, so this is also a slump failure. Slump. So the base flow are the downslope flow of relatively coarse material. 50% of the particle in the debris flow are coarser than sand. Movement may be very slow or very fast depending on topographic conditions. Mud flow, debris avalanche, and debris flow is a type of flow that occur that we consider small to moderate magnitude event, occasional large magnitudes event. Okay, so this is example of rock slide, rock move because there's nothing holding back. Generally required pre-existing low friction surface. Okay, we can see here there is a sandstone overlaid by overlay on a clay bed. Okay. So then there is a limestone under the clay bed. So when the clay bed is exposed to water, okay, it become weak. So then it start to move and then also pull down the sandstone layer. Okay. So this is due to the earthquake. Okay. They call it earthquake leak. Okay. Where in 59, okay, 28 death. Okay. Okay, this is an example to show what happens, okay, due to the uh, the create for the changes of the uh, sea area. Okay, so slope in equilibrium with their environment typically exhibit okay, concave shape convex. Okay, slope out of equilibrium typically exhibit anomalous. Okay, key profile and as shown in the right. Okay, just to show uh, what happened if the slope not either has been eroded, for example. Topography is not necessarily indicative of social instability, but can certainly controlled by underlying stratigraphy. Okay, shell are often associated with landslide. Okay? So there are stepped formation of a different type of material. Okay? If shale exposed to the water, so it become weak and then it may contribute to the um, instability of the slope. Okay, slope that are experiencing rampant erosion are typically out of equilibrium, exhibit truncated concave slope profile. So the slope profile is also influenced by runoff requirement and the relative position of controlling base level. Okay. No change in hill profile as channel move away from the ridge line. Okay. So this is contributed from the rainfall, okay, and also contributed to the river stream. Okay. Okay, this is just to show the changes happen on the hill slope profile, okay, due to the erosions. Okay, so humidity is usually indicative or solid fluction or active length slip piece. Okay, so that's all for the introduction part. Okay, so we take a rest for 10 minutes and then I will continue on the infinite slope. Okay. Okay, take a minute, take a rest for 10 minutes.